Okay, so hello everyone, and thank you for joining me today. My name is Maayan, and I work as a security researcher in Section 52 in the Microsoft Defender for IoT group. I joined Microsoft as part of CyberX acquisition, and before that I worked in a similar role in the Cyber Defense Department in the Israeli Air Force. Okay, so Section 52, who we are. So Section 52 is the Microsoft Defender for IoT research team that expertise in OT and IoT security. And the team is composed of security researchers and data scientists with rich experience in the fields of malware reverse engineering, threat hunting, and protocol research. And today I'm going to introduce to you techniques for investigating malicious programs written in a language named ladder logic. And these types of program run on programmable controllers, or in short, PLCs. And we are going to see later a proof of concept malware I created that runs on Siemens S7 PLCs. And by the end of the presentation, we will see how this malware functions and methods to investigate it and how it can address a new code that was injected by a malicious threat actor. Okay, so before we begin diving into technical details, we first need to understand what the term ICS means. So ICS stands for Industrial Control Systems. And ICS describes different types of control systems and instrumentation, such as devices, systems, networks, and protocols that are being used to operate and automate industrial processes. So these systems are deployed in anything from pharmaceutical to manufacturing. And these systems control many critical processes running around the world. And I'm sure that many of you have heard of different types of them, like SCADA and DCS. So there are different ICS types, different ICS devices that are being used in industrial processes, like PLCs, which function like the brain of the facility and communicate with sensors. RTUs, which are basically PLCs, but designed to work with remote stations. We have safety systems, HMI stations that enable human operators to monitor and control equipment. And last example is data historian that keeps logs for running processes and enable further analysis and statistical evaluation. So surprisingly, there are many of these devices can be found exposed on the internet. And in the following map, we can see ICS devices that were found exposed on Shodan, which is an online search engine that scans the internet for services and devices. Okay, so how many devices do you believe that are exposed in this map? Maybe 100, 500, 1,000 maybe. I can tell you that according to the latest search that we did, we found that tens of thousands of ICS devices can be found exposed on the internet. And attackers can take advantage of this fact and use those devices as an entry point for a cyber attack. So threat actors may want to perform an attack on ICS systems for many different reasons. For example, data exfiltration, deploying ransomware, even causing physical harm. And another important point is that targeting ICS devices, such as PLCs, instead of using an attack regular personal computers, might be an ideal choice for an attacker for different reasons. The first one is that the patch management is hard while there is a critical process running from behind. And another point is that these devices weren't designed from a security perspective. So unlike PCs, PLCs are harder to protect. So to understand how to investigate a malicious program on a PLC, we first need to understand how it works. So a PLC is a type of control system that is being used in automation of machinery processes in an industry. And as I said, it's like the brain of the facility, where it communicates with sensors and machines in the field, and it executes specific logic to control physical processes. So to program on a PLC, a programmer needs to follow a standard, which is called IC 611313. And this is a standard for PLCs. And this standard lists 5 programming languages for PLCs, where some of them are graphical and some of them are textual, where these languages are similar to programs like programming languages of C and assembly. But in this presentation, we are going to focus on one of them, which is called ladder logic, and it's widely used nowadays. So later, I'm going to demonstrate to you a proof of concept malware that I created, that is written in ladder logic. And we are going to see how we can approach an initial investigation of its actions. And it's important to remember that while PLCs are not meant to be used for malicious intentions, we will show how we can utilize their native functionalities for malicious purposes. Okay, so this malware was written in our ICS lab environment, as you can see on the left picture. And our environment consists of many control systems from different vendors. But this specific malware was written for Siemens PLCs, and specifically for Siemens Simatic S7-1200 PLC. But the general logic can run on different versions as well. And I have a final note that the development environment is called TIA Portal. And you can already see in this slide on the right side the main logic of the malware. Okay, so to understand and program a proper ladder logic, we need to be familiar with its most basic units, which are contacts and coils. So a contact is an input and the coil is an output. And in similarity to electricity, contacts and coils can be activated using true or false value. And when they do get activated, a flow can move through them to keep calculate the next unit. So this is like an electricity current. So we can also say that when a coil is activated, we can call it energized and otherwise de-energized. And another note that I have is we can put a slash in the middle of a contact or a coil to perform a logical NOT. And the rest of the concepts of contacts and coils exist in here also. And we can create logical gates using these contacts and coils like AND, OR, NOT, and XOR. And at the bottom line, we can say that a ladder logic program is a set of connections between contacts and coils. So the inputs and outputs in a program may refer to logical tags, structures, and of course, physical devices, as we can see here. And for example, we can use selector switches, motors, and lamps. So a ladder logic program resembles ladders, and we can think of it as a rule-based language rather than procedural, where each rung in the ladder represents a rule. So in similarity to electric circuits, we can say that contacts make or break circuits to control coils, and they control the executed logic. So another important point is that the coil will be energized if and only if a path can be traced between the left side of the rung to the right side of the rung. And in the execution aspect, the software is responsible for executing the multiple rungs of the program, and it does that sequentially in a continuous loop. And when the execution is fast enough, the user gets the effect of a parallel and immediate execution. And of course, this depends on the clock frequency of the processor and the program itself. So as a final note, the program can be executed left to right, top to bottom, and the scan begins at the top left rung, where at the end of the rung, it interprets the output and continues to do so for every rung. Okay, so each iteration in the PLC infinite execution loop is basically composed of reading signals from input devices. After that, performing a program loop and executing the necessary logic. And finally, energizing outputs, calculating the outputs, where this process continues in an infinity loop. Okay, so in this slide, we can see how everything we discussed so far is being used in the actual proof of concept malware when establishing a connection to the command and control server, CNC server. And we can see here that there are two rungs. We have a special block, which is an instruction and that is being used to establish the connection. And we'll get to how it works in a few slides. We have a contact that is being activated and when the connection is being established. And we have a coil that is being energized according to the state of the contact in this same rung. So another very important thing we need to know about is blocks. So Siemens TIA Portal provides us blocks to be used in a program, and we can compare it to functions in procedural programming languages like C. So each block has its own unique role and features, and I will explain about each of them. So the first one is organization block, or in short, OB. And this block controls the execution of the program, and it cannot be called by another block. And that means that only events in the CPU can trigger its execution, like time interval. And there are 15 different types of organization blocks, where the most important one is called program cycle, or in short, OB1. And this is the main block of the program. The next type of block is function block, or in short, FB. And this type of block represents a subroutine with dedicated memory. And that means that it can store its values permanently in data blocks. And so these values will remain for the rest of the execution. The next type of block is function code, or in short, function. And this block has the same concepts of the function block, but it will get executed without dedicated memory. And the final type of block is data block, or in short, DB. And as its name implies, it's being used to store program data. Okay, so if we use this variety of blocks, we can create some very complex logic or subroutines dedicated for specific device or a unique scenario. And here we can see a diagram and we can see here the overall interaction between the operating system and the user program. And we can see how the different blocks can interact with one another. So a program, it's important to know that a program cannot start from a regular block, but from organization block. And this block can call other blocks, and in turn, they can call other blocks as well. And this functionality of using multiple blocks instead of just one organizational block can ease the complexity of the program. And if we look at it from the eyes of the programmer, it can bugs in the development stage. Okay, so instead of programming every needed functionality we need, Siemens provides us with built-in library code blocks that can be called throughout the program. And these code blocks are actually called instructions, and they are implemented from behind using function blocks and system function blocks. And these instructions can provide us with rich functionality, for example, timing, string manipulation, and file handling. And as we can see in the following tables, each instruction can be identified internally by a unique number, and this number will probably vary by firmware versions. So among the many instructions we have, there is a section that is designated completely communication, and we can use those for establish or handle a communication channel. A programmer can use these instructions, for example, to send information between two PLCs or send logs to a remote server. And from a malicious aspect, an attacker can use these instructions to connect to a CNC server, command and control server, to extract information from the internal network to another destination, and the list can go on and on. And as I mentioned before, each communication instruction has a unique number identifier, as you can see in the following tables. And just a final note I have is that these instructions execute asynchronously, meaning that once they are being called, their execution can extend over multiple program cycles. Okay, so in this slide, we can see the usage of TCON as it's being used in the malware code. So TCON is being used to establish communication over Ethernet to a specified destination or a specific port. And in this example, it's being configured to connect to the command and control server on port 2000. We can see that in the lower screenshot. And on the upper screenshot, we can see the instruction block itself. And we can see that it receives inputs and outputs. So I will briefly go over them. And the request is a Boolean flag that determines if the job will get executed or not. ID, each communication channel must have its own unique number identifier. And the connect is the name of the data block that is being used to store information while the block operates. On the output section, we have status flags. We have the done, busy, and error, which are Boolean values. And we have the status, which is the status code of the current execution. So as I said at the beginning, we know why gaining control over ICS systems can be such a huge goal for an attacker. And after we covered basics of ladder logic, we can see that there are two major ways of adding ladder logic to an existing program. So the first method is adding logic to an existing block. So we know that the main block must exist on every program, and it will always get executed. So it's an ideal place for an attacker to inject its malicious logic. Second point I have is that there might be more blocks that will seem strategic for blending into the normal execution. But we need to keep in mind that the attacker will want to do so with minimum interruption, because the PLC owner might notice this kind of changes. And this leads us to the second method, which is adding a new block. So adding an organization block will be probably the most convenient way for an attacker to add its own malicious logic. And as I already mentioned, there are different types of organizational blocks that an attacker can use to achieve its goals. So, for example, we have the startup organization block. And this block will get executed once the CPU of the PLC goes from stop to run mode. And if we compare it to Windows attacks, these techniques remind us of adding a program file path to the startup folder. And another interesting organizational block is time delay interrupt. And this block will get executed at a specific configured time. And the last example I have is cyclic interrupt organization block. And this block will get executed at a specified interval. And in comparison to PC attacks, this technique reminds us of adding a scheduled task in Windows or cron tab in Linux. So there are many well-known ICS cyber attacks, and the probably most famous one, which I'm sure most of you have heard of, is Stuxnet. So Stuxnet is a computer worm that was first discovered in 2010. It was aimed at Iran's nuclear facilities and targeted specifically Siemens S7 PLCs. Throughout the years, it infected tens of thousands of systems around the world, and there are many papers you can read that cover this attack. So among the many actions this malware does, it can change the logic of the PLC. So it changes the main block of the program when it inserts its own malicious logic at the beginning of the block. So its logic will run first. And another block Stuxnet changes is the cyclic interrupt organization block. And this block acts as a watchdog, where on certain conditions, it can stop the execution of the main block. The next malware I'm going to show you is PLC Blaster. And this is a proof of concept malware that was published in 2016. And it runs on Siemens S7 PLCs. And it attempts to locate and infect other Siemens S7 PLCs. It has 4 attack models, which are command and control server, denial of service, SOCKS for proxy, and it can also manipulate the output of the PLC. And the malware logic is stored in organizational block number 9999, where the original code of the PLC remains as it was. So there is no change to the source code of the PLC. The last example I have to show you is InController or Pipe Dream. And this is an ICS cyber attack framework that was publicly published last month. And it's still being investigated. And as part of its many capabilities, it can modify PLC programs and configurations. So as I promised to you, we are now going to dive into the proof of concept malware, which acts as a Telnet brute force scanner. So we first need to know what Telnet is. So Telnet is a client-server protocol that allows remote control of computers via text-based commands. And the motivation to use Telnet in a malware comes from the fact that first, it's widely used, as we can see in the following showdown world map. And second point is that the Telnet communications are sent in plain text, insecure and totally unencrypted. And this fact promises that it does not require any special implementation or configuration like in SSL TLS. Okay, so Here we can see an example for connecting to a Telnet server. And on the left side, we can see the Windows command line just before connecting to the Telnet server. And on the right side, we can see the same Windows command line just after establishing a connection with the server. And we can see the Telnet banner, and we can see a message that requires us to put credentials. Okay, so here we can see the general architecture of the Telnet scanner actions. So I will explain them. So first, the attacker needs to infect the PLC with the Telnet scanner malware. And immediately after that, the PLC will begin the Telnet brute force procedure over the machines in the internal subnet. And it will do so to find valid Telnet credentials. So if a login attempt succeeds, and the PLC will send the found IP address and credentials back to the command and control server. Okay, so here we can see an overview of the program as it's been executed by the PLC. So we can see that at the beginning of the execution, the malware establishes a connection with the CNC server. And after that, the program will try to connect on port 23, which is the default Telnet port. And so it will try to connect on this port to the machines in a predefined IP subnet. And if a connection is made, the malware will perform brute force to the destination, and it will report to the CNC server for any successful login attempts. And at the end, the connection with the CNC server will be closed. Okay, so let's see a part of the malware's code that uses the concept we discussed earlier. So here we can see a part of the routine that sends the Telnet username in the brute force procedure. So first we need to understand how Telnet works. So it works in that way that when we send a single character to the Telnet server, we're going to get it back to us. So here the malware uses tsend instruction to send a single character to the server. And it uses treceive instruction to receive a single character back. So we can see that if and only if a new data received back to us, we can see that by the NDR flag, which means new data received. And only when the expected character equals to the received character, only then the malware will continue to send the next character in line. So here we saw a snippet from this subroutine that sends the Telnet username. Okay, so now we are going to see a short demonstration of the malware execution, and I will stop the video to explain some points. Okay. So when the execution begins, we can see that the connection to the command and control server is being established. And immediately after that, the main logic will be executed. When I say the main logic, I mean that the brute force procedure will be performed over the machines on the subnet. And at the end, the connection with the CNC server will be closed. Okay, so here we have the CNC portal. This is what the attacker sees. And this is where the credentials will be shown back to the attacker after the malware was executed. And we can see that at the beginning there are no credentials in the portal, but after we refresh this page, we can see that the malware did manage to find credentials at valid Telnet credentials at our subnet. So this is it. Okay. So now we're going to discuss about an analysis approach that assumes that the attacker has already managed to penetrate the network. And if they did manage to penetrate the network and inject their own malicious logic, the PLC owner needs to know how to pay attention to some new added unwanted logic. And we also know that each block in the program has its own unique role and features. And we can use this knowledge to know what to look and where. So to be able to detect some roadblocks in our program, we can use the compare utility in TIA portal environment. So we have two options in this utility. We have the offline-online option and the offline-offline option. So the offline-online option allows us to compare between a hard copy of the project that we have to the PLC's loaded project, which is the online project. The second option is the offline-offline option, which means that it allows us to compare between two offline projects that we have, or simply retrieve data about one project. So after choosing an option, we will get a window with information about the blocks that are being used in the project or projects. And as we can see in the middle and the right picture, we can use useful information in our investigation. So, for example, one stands for timestamp interface, which is the last modification time to the block interface. 2 is for timestamp code, which is the last modification time to the source code of the block. 3 is for author. We can look in this column for unfamiliar or suspicious author names. And 4 is another column we can add that is the general modification time of the block. So any changes made to this block, this is the column for it. Okay, so we can detect some unwanted changes by crossing times and validating them. And this can make the PLC owner to be aware of changes in the logic and raise a red flag if something suspicious was found. So on the next 2 slides, we're going to see examples of detecting new added malicious blocks. So if we choose the offline-online option, this means that we are interested in finding changes between project that is loaded on the PLC and an offline project that we have. So here we can pay attention to some 2 suspicious things. So on the left side, we can see that a new logic was added to the main block. And because this is an example, there is no real logic in here, but in theory, an attacker can add its own malicious logic at the beginning of this block, so it will get executed in each program cycle, and just like Stuxnet did. And on the right side, we can see that a new block was added. We can see that its address is OB100, and an attacker will add this kind of block, a starter block, to ensure that it will get executed on every startup of the PLC. And just a side note, generally we can infer the type of the organizational block and just by looking at its address, because organizational block addresses have usually constant values. So it's important thing to know. So in this example, we saw simple ways to identify new added logic and how we can compare an offline copy of a project with the PLC's online project. Okay, so if the PLC owner does not have the original PLC program, or it does not want to rely on it, because, for example, Stuxnet hides the online changes, we can choose the offline option. So we can do this by uploading the program from the PLC and choose this option. So here we can see the different blocks, and we can see that they were modified at different times. And the PLC owner can check for time anomaly and look for changes that are basically seem off. And this is, of course, will raise a red flag for the PLC owner if anything suspicious was found. For example, here we can see that a new organization block was added. Its name is checker, and maybe by its timestamp, it will look suspicious to the PLC owner. Okay, so like in any other malware investigation, it is important to detect communication instructions. And also here in ladder logic, it's important to know how we can look for communication instructions. And now we're going to see some methods to do so. First method, find the usage of communication instructions, is to overview the cross-references of the project. So cross-references indicate which objects are being used by other objects in the program. And if we filter by the instruction object type, we will be able to look for communication instructions that are being used in the programs and which blocks call them. So here we can see that the malware uses the instructions of TCON, TDiscon, TReceive, and TSend. The second method we can use is simply to search for specific communication instruction names in the project. So just note that I have is this search utility looks for any reference in the project that contains the string that we search. So it can also find comments, for example, that contains the search word, like, for example, TCON. But if we did manage to find communication instructions, we will be able to see which blocks use them. That is very important things to know. So another method for finding communication instructions lays on the fact that each one of these instructions requires the use of a newly created data block, because communication instructions need data blocks to store values while they operate. So this is why when a new communication instruction was created, a new data block will be created as well. And we can look for its presence. So if we look under the system blocks and program resources, we will be able to look for any communication data blocks. And for example, we can see on the right picture a data block that is being used by the TCON instruction when opening a connection with the CNC server. Okay, so to summarize everything we discussed about, we managed to learn the basic concepts of ladder logic programming. We saw how a malicious ladder logic program may act, and we saw how we can identify and investigate interesting pieces of code that may indicate about malicious activity. And all of you are welcome to join our IoT security community and stay up to date in the IoT cybersecurity field. You can do this by typing the link down below or scan this QR code. And me and others in my group will be happy to answer for any related questions you may have, if it's about collaborations, incident response services, and the products we offer. So that's it for today, and thank you all for being here today. If there's enough time and questions, I'm here to answer. And that's it. Thank you.
Great. Yeah, thank you. We do have a few questions. First one is there any way to do white box testing on block logics? I mean static analysis in order to find the eventual vulnerability before deployment.
I believe that yes, like any other program in other language. We are working on it. We still don't have this ability, but we will definitely going to do that.
Great. The next one is, how does malware hide online changes in PLC?
Okay, so if I will give example like Stuxnet, this specific attack deployed a DLL that was in use in the Siemens development environment. And this DLL was responsible for the communication between the PLC and the development environment. So this is how Stuxnet managed to hide any online changes because of this specific DLL.
Great. The next one is more of a comment. It seems to me that the important thing is to make sure that the code doesn't get changed with approval. Any unapproved change should be considered dangerous. It does not really matter what the change was.
Definitely. I definitely support this comment, and I think it's like any other program we deploy, whether it's on PLCs or PCs. It's important to pay attention what we add to our program.
Great. And then the last one is, are there code management systems for PLC code?
What does it mean, code management systems?
We will probably have to offline that one, but that's all the questions that we had. So I'd like to thank you, Maayan, for being our guest today and for an excellent presentation. And thank you to the rest of the team who helped answer questions. At the same time, I would like to remind the listeners that the best way to ensure you don't miss any future webinars or major announcements is to visit our landing page at aka.ms/securitycommunity. And while there, you'll find easy ways to navigate and find the resources and learning content relevant to our security products and their communities. A good start would be browsing our bite-sized product videos, ninja trainings, recordings of past webinars, GitHub communities, and more. We'd love to hear your feedback on how we can improve these webinars. Please take a minute submitting your webinar feedback at aka.ms/security webinar feedback. Thank you and see you next time. Goodbye.